Welcome back. Section 5-2, the definite integral. Let f be a function defined for x between a and b, closed interval a to b. We divide the interval closed interval a to b into n subintervals of equal length, equal width, delta x, b minus a over n, that is the total length over n. Let x sub 0 be a, x sub 1 be a plus delta x sub 2 be a plus twice delta x sub 3 be a plus 3 times delta x, so on, x sub I be a plus I delta x, all the way to xn equals b. Then we obtain n intervals x0 to x1, x1 to x2, x2 to x3, and so on. The ith interval is x sub I minus 1 to x sub I, and the last interval x sub n minus 1 to x sub n. Let x1 star, x2 star, x3 star, xi star, xn star be any sample points from the intervals respectively. That is, x1 star comes from the first interval, x2 star comes from the second interval, so on. Sample point means any point from the chosen intervals. Then the definite integral of f from a to b, it is denoted in this fashion: definite integral a to b fx dx is limit n approaching infinity, summation I going from 1 to n, f of xi star delta x. If you remember the right hand side, this is precisely the limit of Riemann's sum, which is area between the curve and the x-axis over the given interval a to b that we have been learning. We learnt in our previous section. So this definite integral is defined in this fashion provided that this limit exists and gives the same value for all possible sample points. So sample points could be any point from here. You could choose any sample point. You could choose left end point, right end point, midpoint, any other point. Okay? If this limit exists, we say f is integrable on closed interval a to b. Note the summation I going from 1 to n fxi star delta x, it's called the Riemann sum. Therefore, the definite integral is the limit of the Riemann sums as n approaches infinity. The symbol, it's an elongated s, it is called the integral. It is an elongated s to represent the sum. The numbers a and b, that's this a and this b, are called the limits of integration. The number a is the lower limit. The number b is the upper limit. The expression fx in here is called the integrand. The expression dx informs us that x is the independent variable in the function f. Geometrically, we may understand the definite integral as the area with sine. We will see in a minute what that means. Area with sine between the curve and the x-axis over the given interval. This area with sine is called the net area. That is, if your curve were like this, above the x-axis, then this is the area. This is the definite integral. Integral a to b fx dx is precisely this area a, where a is positive. But what happens if part of the curve is below the x-axis? You see one area here, you see another area here, and yet another area here. Then the definite integral a to b fx dx is this area minus this area plus this area. So any area above is added, any area below is subtracted. So notice all the areas are precisely positive, but the net area is all the areas above are added up, all the areas below are to be subtracted. Okay. Evaluate the Riemann sum for fx equals x cubed minus 4x for 0 to 3 with n equals 6 subintervals and taking sample endpoints to be right endpoints. So notice they are simply asking for Riemann sum. They are not asking for limit. They are not asking for definite integral. At present, they are asking for Riemann sum with 6 subintervals over the interval 0 to 3. In theory, you don't need to draw the graph for this question. But as a practice, it's always a good idea to graph the function. So y equals x cubed minus 4x looks something like this. As you can see, it is not really in scale because here is 3 and here is 15. The height is 15, so it's not in scale. Now I'm going to have to use right endpoint. So I've drawn these rectangles, you see, using right endpoint for the first interval, right endpoint for the second interval, right endpoint for the third interval, right endpoint for the fourth, for the fifth, and for the sixth. Notice there is a substantial area below and some area above. So let's see how this looks like. So goal is to use n equals 6, that is 6 rectangles over the interval 0 to 3, and this is your function. We are supposed to take right hand points. Okay, summarize that. So the interval under study is 0 to 3. We want to divide this interval into 6 subintervals of equal length. So length of each subinterval will be total length 3 over 6, which is half or 0.5. Starting from 0, the 6 intervals are 0 to 0.5, 0.5 to 1, 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3. These are your 6 intervals. The sample points are supposed to be right end points. So the right end point of the first interval is 0.5, from the second one is 1, from the third 1.5, from the fourth 2, from the fifth 2.5, from the last one 3. What is the Riemann sum? It is sum of the areas of these rectangles. In other words, for each area, each rectangle, area is width times height. Width, if you remember, is 0.5. Height is given by your function on your sample point. So, 0.5 width times the height for the first rectangle, sample point is 0.5, plus 0.5 times f at 1, plus 0.5 times f at 1.5, 0.5 times f at 2, 0.5 times f at 2.5, 0.5 times f at 3. I have used the expression x cubed minus 4x. I have plugged in this x value and I have found these values. Okay. So I have applied x equals 0.5 in your function to get this number and so on. This is my final answer. Okay. So this is just the Riemann sum. Here is a theorem. If f is continuous on closed AB, or if f has only a finite number of jump discontinuities, then f is integrable. That is, the definite integral a to b fx dx will exist. What does that mean? Remember, the limit of Riemann sum may or may not exist in general. But this theorem states if f is continuous or if f has only a finite number of jump discontinuities, then this integral does exist. The limit will exist. Here is an example of jump discontinuity. Your function is continuous here and then jumps. So it's a finite jump. It doesn't go to infinity or negative infinity. It jumps just a little bit. Jumps up or jumps below, doesn't matter. It has a finite jump. Such a function, your limit will exist. So integral a to b, in this case, what do? For each piece, find the area and add them up, assuming these areas are positive. If your curve were to jump down, then you would subtract that area. Next theorem. If f is integrable on closed interval ab, then a to b fx dx is limit n approaching infinity, I going from 1 to n summation fxi delta x. What is fxi? Xi is a plus I delta x. What is delta x? That's the width of each subinterval. Notice xi basically is the right hand point of each subinterval. Okay, so this theorem states you don't have to choose midpoint, left hand point. You don't have to make such decisions. If you just take the right hand point, it will work just fine. Let's recall a few summation formulae before we proceed. Summation I going from 1 to n of 1 is n. Summation I going from 1 to n of I is n times n plus 1 over 2. Summation I going from 1 to n of I squared is n times n plus 1, 2n plus 1 over 6. Summation I going from 1 to n of I to the power 3 is n squared, n plus 1 quantity squared over 4. So these formulae are to be memorized. Let's recall some summation for properties. Summation I going from 1 to n of a constant times ai, the constant can jump out. Notice the constant is not dependent on I. A is dependent on I, so A has to stay in. But C is not dependent on I, so it can jump out. Summation I going from 1 to n of ai plus bi. Well, summation will split. Summation I going from 1 to n ai plus summation I going from 1 to n of bi. Likewise, summation I going from 1 to n of ai minus bi, the summation will split. Summation I going from 1 to n ai minus summation I going from 1 to n bi. Let's continue then with the next problem in our next video.